Previously in Chapter 12, we've gone over sound waves and sound intensity and resonance. Now we're moving on to the final segment, which is harmonics. In the last chapter, I went over standing waves, which are patterns that can be produced on a vibrating string. As you can see, these three are all examples of standing waves. The first has one antinode, the second has two, and the third has three. And again, from the last chapter, antinodes are simply the bulges that occur along the string as these standing waves are produced. In the situation of sound vibrations, the length of the string accounts for 1/2 of the wavelength, or lambda. This is because if you visualize a sine curve, this entire cycle would be the wavelength, whereas in this string we only have half the cycle. And we know that velocity is wavelength times frequency, so I've rewritten that by dividing both sides by lambda to find that frequency is equal to velocity over wavelength. This leads us to our fundamental frequency equation. We know that lambda, or wavelength, is equal to 2L. So we plug that into the bottom, and then we have this n. N is the harmonic number, which is simply another factor in determining the fundamental frequency. And by the way, the fundamental frequency is defined as the lowest frequency of vibration for a standing wave. So this is essential to determining frequencies of instruments and other things that emit sound. So this will be our equation for fundamental frequency. We have F equals NV divided by 2L, where L is the length of the string. In addition to strings, fundamental frequencies can also occur in a pipe or an air column with the same equation, where if we have an air column of length L, the fundamental frequency will equal N times velocity over 2L. Now the only difference is if the end of the pipe is closed. So let's say this one end is sealed off. Now, only odd harmonics are present. So we would have to say that fundamental frequency is now equal to velocity over 4L, because half of the harmonics are cut off. Harmonics also account for timbre, which is the musical quality of a note. The spectrum of sound is the mixture of harmonics that produce the characteristic sound of an instrument. So each instrument has sort of a distinctive noise, and that's produced through the fundamental frequencies and the harmonics of the instrument. Fundamental frequency also again determines pitch of the instrument, as we've discussed before. And finally, one last concept to define are beats. Beats occur when two waves of slightly different frequencies overlap, so in other words, creating superposition as I've drawn below. And there becomes periodic variation in the amplitude of the resulting wave. So below I've drawn this wave that gets wider and wider towards the middle and then narrower once again. And this wider spot occurs at this place where the two waves completely match up. And that also causes a variation from loud to soft in the noise. Now let's do some practice problems. Number 1. What is the fundamental frequency of a 0.2 meter long organ pipe that is closed at one end when the speed of sound in the pipe is 352 meters per second? So this involves the equation for fundamental frequency, where F is equal to V over, and then in this case, since the pipe is closed at one end, it'll become 4L. Now we're ready to solve for fundamental frequency. So the speed of sound is 352 meters per second in this pipe, and then divided by 4 times, and then 0.2 is the length. Simplify all of this, and we get that the frequency is 440 Hertz. For our second problem, a violin string that is 50 centimeters long has a fundamental frequency of 440 Hertz. What is the speed of the waves on this string? So this time we're using fundamental frequency again, but since it's for a string, we just have V over 2L. Now we know that the fundamental frequency is 440 Hertz. The velocity is what we're solving for, and then we have 2 on the bottom times 0.5, because this measurement was in centimeters, so we have to convert to meters. Now 2 times 0.5 will just become 1. So if 440 equals V over 1, then V equals 440 meters per second. That's the speed of the waves on the string. This has been Chapter 12 of Physics. We've discussed sound waves, gone over sound intensity and resonance, and finally we've looked at some harmonics. Thank you for watching.